Another presentation all ready to go. Let's head over to Andy here. And Andy, survival and reliability analysis, brand new in Mathematica 9.
Yeah, kind of a totally different topic from the social network analysis, but survival and reliability, nonetheless, very important topic. And I want to share with you some of the new things that we have in version 9 for that. So let's look first at survival analysis. Well, what is it? Survival analysis is it's modeling of time to event data. And oftentimes that event is something very dire like death in biological organisms or failure in a mechanical system, but it doesn't have to be something dire like that. It could be the time to your first employment after going to college, for example. So oftentimes that event that we're interested in, the exact time that it happens isn't exactly known to us. So we might only know that the event happens on some interval. In that case, we would have what's called censoring. Or we might only be aware of individuals over some particular interval. And in that case, we have what's called truncation. So there's this special data for survival analysis, and we need ways to handle that. Just to give you kind of a graphical representation of censoring, what I'm talking about, we have a matrix plot here. The squares represent events where we know exactly what time that event happened. So like in this case, this event happened at time 10, say 10 weeks. But then we also have events here that are called right-censored. Notice that they're open on the right-hand side. This means that there's a lower bound, in this case 11, at which that event could have occurred, but then we don't know exactly when it happened. So maybe this is someone was on a study and we were following them until their death and they didn't die by the end of the study, so we don't know when that might be. So we're going to look at some new tools for survival analysis in Mathematica 9. And I'm going to go over a couple of practical examples, time to failure for cooling fans, and survival of patients with cancer of the larynx. So first, the new tools for working with survival analysis. Now, I don't have time to go over everything that's there, so this is just sort of a brief overview. But some of the really key concepts are how do we actually get this censored and truncated data into Mathematica in the first place? What kinds of models can we fit with it? And then what kinds of special hypothesis testing functions are available for working with survival data. So to get our data into the system, we have a function called event data. And this is effectively a wrapper that lets us work with censored and truncated data, just like it's any other data in Mathematica. So here's an example where I have two arguments being fed to event data. The first argument are the event times. So let's just say that these are measured in weeks. This second one could be 23 weeks, for example. The second argument to event data here is a list of censoring indicators. In Mathematica, a 0 indicates that the individual died or the unit failed or something like that, and a 1 indicates right censoring. It didn't fail by the end of the study. So once I enter that into the system, I can work with it just like any other data. So I can compute descriptive statistics with it. For example, here's a 5-number summary computed with quantile, just directly on that event data. I compute a probability. What's the probability someone survives longer than 22 weeks, say? Or here is an expectation, which is actually a mean residual life computation, saying what's the expected lifetime beyond 22 given I survive at least that long? So another 2 weeks, 2 years, whatever. So we can compute these descriptive statistics and probabilities right out of the box, but we can also fit models with this pretty directly. So estimated distribution is something that we introduced in version 8 that allows us to estimate parameters for all of our many parametric distributions. We can do this with event data just fine. So here we have a Weibull distribution, which is very commonly used in survival analysis, and I get a maximum likelihood estimate out. We can also do non-parametric estimates. So here's a kernel density estimator. I have a bandwidth parameter h. I'm leaving that symbolic, and the reason for that is so that I can let this bandwidth or smoothing parameter vary. What I'm seeing in this manipulate is the non-parametric kernel density estimate of the survival function. Notice it's a step function right now that looks something like a Kaplan-Meier estimator, for those of you who are familiar with that. And I have my parametric Weibull estimate of the survival curve. Now, I can let this bandwidth vary, and what that does is, as it gets larger, I'm smoothing out my non-parametric estimate. So as it smooths out, it starts to look more like the parametric estimator. So that's great. We can do all of these things just right out of the box with event data. But in survival analysis, there are a lot of more interesting and advanced kinds of analysis you might want to do. For example, you might want to have confidence intervals about some of these survival probabilities. You may want to perform some kind of regression and get diagnostics and residuals and these sorts of things. So we've added in 9 survival model fit and Cox model fit to do just these things. So here is a survival model fit of my event data that I've been working with. And what this allows me to do, it's kind of like linear model fit that we've had around for a while. It lets me query all sorts of properties once I've fit the model. So this manipulate here, I'm hiding the code. I just have a survival model fit, and I'm extracting point-wise bands and an event table, and then plotting the survival curve. So let's look at what that does. Got the survival curve, the point-wise confidence intervals about those survival probabilities, and here's the event table that came out. I've actually linked this up so that we can vary the confidence interval, or the confidence level, and as that confidence level gets large, the intervals get larger as well. So Cox model fit and survival model fit have a number of hypothesis tests sort of built into them as properties, but there are other kinds of tests that we might want to do that maybe fit sort of outside of that range. So we have this function log rank test that is built in to be able to compare hazard rates and survival functions for different groups of event data. So here I have a couple of event data objects. Enter those into the system. I can see visually that the survival functions look different, but that's not a statistical measure. I might be interested in saying, okay, well, is that difference statistically significant? Well, that's where log rank test comes in. So here I'm going to perform a log rank test and produce a test data table. At the 5% level, I would say that there's a significant difference in the hazard rates for these two populations. Okay, so that's a taste of the new kinds of stuff that's there. Let's look at some applied examples for how to actually use it. So this first example is time to failure for cooling fans, and these are computer cooling fans. So say I have a collection of 70 such fans that I've selected for testing, and at the end of the study, 12 of those fans have failed. That means 58 of them are still around and still functioning. Well, I don't want to just throw that information away, so this is where the survival analysis and handling censored data comes in. These are write censored data. And that data is just stored in my event data object here, and I'm estimating an exponential distribution for those fan lifetimes. And the plot that comes out here using survival model fit against the exponential looks like the non-parametric and parametric estimators agree reasonably well. Once I've fit this model, in this case I'm using the exponential distribution, I can compute all sorts of things from that. So this is the median time to failure for fans, about 17,000 hours. And this is the probability that a fan lasts longer than 8,000 hours. It's about 0.72. So here's more of a sort of clinical example. Survival of patients with cancer of the larynx. This is a famous data set in survival analysis. We have 90 male patients, and they were diagnosed with cancer of the larynx at a certain age, and they are each in one of 4 stages of cancer, with stage 1 being the least severe and stage 4 being the most severe. Kind of hiding the data from you, but this function Cox model fit, which is an extension of survival model fit to allow for other explanatory variables, I'm going to use that to create a model here. So notice that I have these variables stage and age. That's actually what's coded up in my covariates. Stage of cancer, age at entry to study. Serve here is the actual event times, the censored data. So I have nominal variables goes to stage. The reason for that is because stage is actually not something I would want to treat as numeric. It's a categorical response. So this allows me to treat it as a categorical variable. Let me make sure that I have that entered. Once I've done that, this model that comes out works very much like a linear model fit. I can extract all sorts of properties. One that I think is really interesting and important is this parameter table. It has lots of good information stored in it. So the parameter estimates themselves, something about how significant those parameter estimates are. And the column that I find most interesting is this relative risk column. So with a Cox model, we're always comparing to some baseline. In this case, we're comparing everything to those with stage 1 cancer. So what this is showing, so for example, this parameter estimate is highly significant. The relative risk for stage 4 is 4.44, or 5.44, which means people with stage 4 cancer are 5.44 times as likely to die as those with stage 1. So it's much better to be in stage 1 than stage 4. Now, unlike a lot of other software packages, we actually have made it possible to easily visualize the survival curves from our Cox models. So here what I'm doing is showing the survival curves for the 4 different stages of cancer, and I'm allowing the age at which the individuals entered the study to vary. So coming in at an early age and being in a low stage of cancer is the best prognosis. If I come in at a later age and I'm in a higher stage of cancer, that's bad news. And we can see that this is all acting pretty quickly and smoothly. All right, so that's it for survival analysis. Now I want to talk about a related topic, reliability analysis. Reliability deals with independent components that are connected into a bigger system. While we're interested in, we know something about the survival of those individual components, and we call that the reliability of the component. So reliability of a component is the probability that that component's functioning at a given time. Reliability analysis allows us to take these components with these known distributions, connect them together, and say something about how long the system itself is going to survive. So here's just a diagram to give you an idea of what I mean. Say we have a process that we want to get through from start to end. We have 3 components in this case, and in order to make a path from start to end, D1 has to function, and either D2 or D3 do. So I'm going to talk about some new tools in Mathematica 9 for doing this, and I'm going to show a couple of application examples, reliability of computer processors and the reliability of a car. So these new tools that I'm going to cover, and this is by no means all of what's there. There's a lot more, and I'll point you to a link later. I'm going to talk about some models that are very powerful, reliability distribution and standby distribution. So let's start first with reliability distribution. So given that we know the reliability distributions of the components, and we know something about how they're connected together, we can use reliability distribution to say something about the survival of the entire system. So here's that same picture that I showed before with the 3 components, where D1 has to function and either D2 or D3 do in order to get to the end. We code that up in reliability distribution as such, D1 and D2 or D3. And I see that I'm giving component distributions for each of the components. So these are all exponential, and they have various lambda parameters. So this is all symbolic. I expect my mean time to failure to also be symbolic. And I can compute the survival function, or in this domain, we would call it the reliability function. Another model that's new to 9 is standby distribution. So sometimes you have a component that is either really likely to fail, so what comes to mind would be fuses, or you have a component that if it fails, it's just catastrophic. So I think of O-rings in a space shuttle, for example. So what we do in those circumstances is try to build up a bunch of backups that are redundant, that'll kick on when one of them fails. So that's what standby distribution allows us to model. These backup components are activated when one of them fails, and here what we're going to see is a cold standby system with imperfect switching. So standby distribution lets us work with cold and warm standby. Cold standby means that the component doesn't start to decay or until it's actually been activated, whereas warm standby means that it's actually decaying as soon as the whole system's activated. Imperfect switching, what this P parameter means, it's the probability that I effectively switch over from one component to the other when one of those components fails. If I had perfect switching, it's just going to switch right over and have no trouble with a probability of 1. So here, I'm going to look at the mean. Again, it's going to be symbolic, and the survival or reliability function. The cool thing is that standby distribution can actually be used as a component in a reliability distribution. So extending that picture I showed a little bit before, we still have D1, D2, D3, but now I'm allowing for backups for D1. So now as long as any one of these D1s kicks in and works, I'll make it to the choice of D2 or D3. And this manipulate is showing what the reliability function looks like for this system if I have different numbers of backups. If I don't have any backups, the reliability is low, and as I increase the number of backups, the reliability of the entire system increases. So an application example, we're going to look back at the fans that I was talking about in the scope of computer processors. So suppose that a computer processor has 2 cooling fans, and one of those fans has to operate to keep the processor from overheating. So we're going to bring back that data on the cooling fans that I had with the survival analysis part and get that estimated exponential distribution. And I'm going to use those that I've estimated from event data, and I have to say at least one of them has to work in order for this system to not fail. So the median survival of the fan itself is about 17,000 hours, as we saw before, but now that we have two of them, we have 30,000 hours median survival for the whole system. And because this is a distribution, we can do things like simulate it. So here I'm going to simulate processor lifetimes until they overheat, 10,000 of them. It's pretty much instantaneous. Okay, the reliability analysis of a car. So this is a very simple model for a car. The idea is that if I start at my starting destination, or starting point, and I need to get somewhere safely, there are several things that have to work. My wheels have to work, my engine, my transmission, and one of my two brake systems. All modern cars have two brake systems. So we code this up in a reliability distribution saying the wheels and the engine and the transmission and one of the brake systems have to work for me to get safely where I'm going. Now this is all symbolic, but let's add some numbers to get a sort of realistic model. This is the mean time to failure. I'm using expectations in expectation here with those parameter values plugged in. This is how long I expect a car to last, assuming I perform zero maintenance on it. So about 3 years with no maintenance. And hopefully it's not the brakes that fail. So now let's do, since this is a distribution, why don't we just simulate some time to failure for 100 cars. The horizontal line here is showing the mean time to failure, and we see that many of them are above that and many of them are below it. So I didn't have time to cover very much information here at all, but there's a whole lot of information out there online for you to access. One good place to look is at our new and 9 pages. This one for survival analysis has a lot of the, not only examples that I showed here, but a host of other ones, and gives some taste of the kinds of things that you can do. We also have one for reliability, and then we have guide pages, which give a rundown of the different kinds of functions that we have in Mathematica for this particular domain. And you see that reliability covers a whole lot more than just the two pieces that I introduced here. And that's about all I have, Zach.
Well, Andy, I guess one question that I have for you right away is, you mentioned the right censoring examples. What sorts of other censoring and truncation can you work with inside Mathematica 9?
That's a good question. Okay, well, we can actually work with a whole range of, I talked about censoring being an interval. Right censoring can actually be specified as an interval from some time t to infinity. We can be fully general about that. We can say left censoring from minus infinity to some time t, or we can say interval censoring from t1 to t2. We can do the same level of generality with truncation, and we can mix and match those things any way we want. And actually, if we look at the documentation for event data, there's plenty of information on how to get all these different kinds of censoring into the object. Let's look, pardon the scrolling. Yes, specifying censoring and truncation. So each and every kind of censoring and truncation that's handled by event data is documented there in what I would consider very simple examples to show how to get just that kind of censoring into the system.
Nate, a lot of the examples that you've shown here have used small data sets. How well does this scale to much larger data sets?
Well, let's see. So yeah, I agree. We use the small data sets because they're kind of cleaner and easier to look at, but I can just try to create something here. Let's just say that I had data as random variate from, say, an exponential distribution and do, I don't know, 100,000 of them. And I'll say that my censoring indicators are a random choice, 0, 1, so I'm going to have right censoring, and I want 10 to the 5th of those. So now let's do a survival model fit of my event data sends. Takes a little bit, but it's done. And now let's do a plot of that survival function, where t goes from 0 to 25. And we'll say exclusions goes to none. Pretty rapid. So it scales relatively well.
It looks like it did scale pretty well. Well, if you want to know more about that or find some examples, head to the Documentation Center. You can also learn more at wolfram.com/Mathematica.